Okay, so welcome everyone. Welcome to the seminar. So I'm Qingpeng of IDS, and today it's our great pleasure to have Professor Yunbei Xu from AOS, Industry and System Engineering. So to give a brief introduction to Professor Xu, he's an assistant professor and actually the presidential young professor, one of the most prestigious title for the junior faculty members in AOS. And he received a bachelor degree in pure math from Peking U and a PhD in decision sciences from Columbia. And his work, he also did a postdoc in computing at MIT, so all the best places. And his research connects mathematical foundation, AI, and the physical systems. And he's also recipient of the ICML Outstanding Paper Award and in the CS committee, and the first place in the Informs student paper competition in the IEOR community, really the rising star in both worlds. So today the topic is pointwise generalization in deep neural networks. Okay, so let's welcome Professor Xu.
Hello everyone, so it's my great honor to come here to give this talk at Hong Kong University. So as you can see, the paper was posted in arXiv this month, and also this is the first talk I give about this paper after the whole project is finished and posted online. So this event is also a milestone for myself on this project. So this is a joint work with my brilliant postdoc Shaojie Li, who began working with me on this project starting 2 years ago. Shaojie is going to be an assistant professor at the Renda Gaoling School of Artificial Intelligence next fall. So we are very glad that we can finish this a long project and get some really good results. And this is the thing that I want to share with you. Okay, so the title of this talk is Pointwise Generalization in Deep Neural Networks. So in this talk, we want to propose a new generalization foundation for deep learning and neural networks. So the background is that a central question in deep learning is why over-parameterized neural networks generalize well. We have seen that the deep learning models is becoming more and more heavy, and there are more and more numbers of parameters, initially from the fully collected neural networks to ResNet, then to transformer and the GPT models. So there are billions of parameters. However, despite that there are huge number of parameters, the models still have very good generalization performance, and this has become a central mystery of deep learning from the mathematical viewpoints. I would like to briefly mention why we want to complete and transparent mathematical theory for deep learning. We all know that there is limited theoretical understanding in this topic, and many people treat it as a black box. However, although we do not claim that we turn this black box into white box, but we really believe that this puzzle is great opportunities for theoreticians and mathematicians to work on this topic, because this is like in, for example, when there are inconsistencies between the experiments and theories, and when there are intractable models, then there is great opportunities for the mathematicians to develop new mathematical branches. We do believe that this kind of highly non-convex and highly nonlinear models can be a source of inspiration to applied mathematics and even pure mathematics, just as what quantum mechanics has done to mathematics in the last century. So this is from a very personal and very theoretical view on why this a great puzzle is also a big opportunities for theorists. The second thing I want to comment is this widely spread view from practitioners and scientists that like we cannot explain deep learning. However, there is really need for reliable AI because even until now, like although we can use AI to generate conversations and to predict classification of images, if we want to apply deep learning to auto driving problems or medical problems or high stack decision making problems, then we still need more reliable guarantees with more rigorous justification. So for this reason, we still believe like establishing a very predictive model for deep learning is one of the greatest tasks for modern science, and this is a big topic. So this work is only a small step, like trying to make progress in this direction. This slide just want to re-emphasize that although now the empirical AI is becoming very successful, it is still very important to review the foundation and trying to see what mathematics can say for those deep learning models. Okay, so today we'll have 3 parts. The first part is like the most important part. In the first part, I will review our central results. That's called the generalization in deep learning. I will review what we prove and what we observe in experiments and how to understand our results. The second part is called a trilogy of principles. Basically, you can understand this as like the 3 key steps to prove our main results. So so the second part is like quite technical, but I will try to explain them in the basic natural language to make you comprehend, to make you appreciate like how this is proved. Then the third part I will talk about the experimental results, which is more easy to get, like the main message of the discoveries. Okay, so let's begin the first part, also the most important part, the generalization in deep learning and the neural networks. So here I want to review the fully collected networks, which is the central object we study in this paper. So I would like to emphasize that in this work, we do not study CNN or RNN, we just study the fully collected networks. So here we can see we have different layers, and at each layers, there are different nodes. And between nodes, there are connections and weights. Because, for example, because they are like the input dimension and output dimension for each layer, so the weights between the nodes on 2 adjacent layers can be expressed as a matrix. So here, each matrix, for example, the matrix at the IO layer is the DL times DL minus 1 dimensional matrix. And also all these sigma functions, they are nonlinear activations. For example, the ReLU activations. And in this work, we assume all these activation functions to be Lipschitz functions, which is satisfied by the ReLU activation. And this is like the most basic mathematical model for deep learning. I think you may all be very familiar with this like fully collected network, but you may also be curious about how we study this mathematically. So yes, just as mechanics, we also have a very rigorous and precise modeling of this fully collected neural network. That is to express each weight by a matrix. And the matrix, the dimension of the matrix is the input dimension times the output dimension, which basically describes all this like a linear combination within layer. However, the great nonlinearity of the neural network actually comes not only from the activation function, but more from this composite function structure. Even if all these activation function identities, the model is still highly non-convex and highly nonlinear because we have this very complex composite function structure. If you multiply the first weight by the second weight and then the third weight, then eventually this network will become a very nonlinear function which have a very irregular landscape. And this makes the analyzing of this model to be very difficult because traditionally we know that statistics centers on linear models and optimization also centers on convex functions. So the inability of existing mathematical tools to study these very non-convex models and very nonlinear model and or the composite models is a great source of inspiration for us to develop new mathematical tools. And in this work, the fundamental concept we want to discuss is called the feature matrix. What is feature matrix and what is feature map? Okay, so now it's like we not only care about the output at the last layer, we also care about the output at the central layer. For example, at the I/O layer, we say the output FIO WX is the depth I/O feature map. And because we have n data, because we have train and n training data, so if we treat each input as columns, then we can combine these feature maps into a feature matrix. So this big FIO WX is called the feature matrix. So the feature have physical meaning. For example, in computer vision networks, in the initial layers, you learn triangles and rectangulars. And in the later layers, you learn eyes and nose. So that's like the how the representation evolves along the layer. And in this work, like key characteristics of our bound is that we depend on the representation complexity, that's the effective rank of the feature map and the feature matrix for every layer rather than just the output layer. Okay, so now this is like one of the most important slides in this talk. If you understand this well, then you understand the majority of what we are proving. So what we are proving is a very surprising generalization bound to me. So first, what is generalization bound? Generalization bound is the gap between the test error and the training error. We all know that in deep learning, we want to make the training error to be very small. So as long as we can further control the gap between the test error and training error, then we will have a rigorous guarantee for deep neural networks. And so the right-hand side is the generalization bound, basically characterize like what is the envelope of the left-hand side generalization arrow. So this is different with the traditional generalization bound because this is like a function of W. So this is an envelope of W rather than a scalar value bound. So both the right-hand side and the left-hand side are functions of W. So the right-hand side will change for different W. For some W, the right-hand side is small. For some other W, the right-hand side may be big. So what's the particular meaning of the right-hand side? So here we can see that like we have this kind of the typical 1/n scaling. So for people who are not familiar with generalization theory, this 1/n scaling is typical, meaning that as long as you have more number of examples, as long as you have more data, your generalization gap decrease, means that the generalization error is small. And the remaining part is similar to the number of parameters in the sense that we have this sum over all the layers. And in the first part, we have this is like the sum of the column dimension and the row dimension. So basically, this is like one part. The other part is actually the effective rank of the Gram matrix of feature map. So this is called the feature Gram matrix. Well, so first, immediately we understand that like if this effective rank is just the ambient dimension, then the right-hand side is just the number of parameters. Then this bound is reduced to the number of parameters divided by n, which is a traditional statistical learning bound, but not enough for deep learning. Because in deep learning, we know that the number of parameters is typically very large. So at least we know that this bound is an improvement of the traditional statistical learning regime where the complexity is the number of parameters. But however, here the complexity is much better than the number of parameters because the complexity is actually a pointwise envelope where as long as you have very good compression, as long as you have good feature compression, you get a very good generalization performance. Okay, so in particular, this effective rank is a smooth notion of rank. Basically, this is like the number of meaningful directions the feature data actually occupy as a layer. If you observe empirical experiments that like the feature learns the eyes, the noise, as long as you know the high-level feature, you will have that like the, although the feature map have big dimension, but it will only have like a few meaningful dimensions. So in this sense, a compression on feature map means that the rank of the feature map is low. Because it's a smooth notion of rank, so the soft rank is much smaller than the hard rank. And the hard rank is already smaller than the ambient dimension. Okay, so here we have a rigorous example in our paper that when the features are strict low rank will exhibit a rapidly decaying spectrum that is like a few large eigenvalues dominate many small ones, then the effective rank is small. So the bound remains tight even for over-parameterized very wide and deep networks. And this is like the main result proved in the paper. So we understand that this result is much stronger than traditional generalization bound because the right-hand side is even lop, a function of the weight. And also like it uses a soft notion of rank. The soft notion of rank is much smaller than the hard notion of rank. And the hard notion, okay, soft notion means that as long as like you have only a few meaningful eigenvalues rather than non-zero eigenvalues, then effective rank is small, and the hard rank is like the count of non-zero eigenvalues. But even this hard rank will be much smaller than D. So we understand like this result is like provide a justification of the representation learning in the very non-convex and non-linear regime. So I would like to comment that like there is a central open question like in the learning theory community to characterize the nonlinear feature learning regime. Like when training the deep neural network, and we believe this bound partially solve this question because along the dynamics, like this is like a pointwise version of this kind of neural tangent kernel or anything that uses linearization, because this applies for all weight. This is uniformly over all weight. So there is essentially no initialization or linearization or no like infinitesimal approximation or infinite wise approximation, but also like being valid at every point. The final thing I want to comment is that this notion, the effective rank of the feature, is also much more fresh than the old complexity notion like sparsity or norm, because sparsity and norm, they are properties of the weight matrix themselves. Sparsity is the non-zero ingredients of the weight matrix, and the norm is just the scale of the matrix. However, here the effective rank is for the moving feature matrix. So this is a completely different regime. So being able to study this feature compression is like completely new compared with being able to study like a sparse or like a low norm compression, because from a covering number angle, all this sparsity or covering over low norm like complexity can be controlled by traditional covering number and uniform convergence approach. It's just like how you compute them and how you select the proper space. However, being able to control the complexity via the feature compression with extremely wide and deep networks, this requires completely new technology from differential geometry and the stochastic process, which I will detail shortly. Okay, so here I also want to give like the particular notion of this soft effective rank. This soft effective rank is just the number of eigenvalues that is greater than a threshold epsilon. And in our final bound, we will optimize this bias epsilon with this like with this effective rank bound to recover the final generalization results. And I would like to compare like our results with several existing results. So first, there does exist this kind of global bound. The global bound means that like valid at every point rather than the initialization. Deep learning is nonlinear, so for people who are not familiar with the theoretical background, I would like to review that like the most popular method in deep learning theory is to you select an initialization point and you do Taylor expansion around the initialization. So around the initialization, because of Taylor expansion, you have an approximate linear model. And this linear model, you can apply the linear theory of statistics, just applying the generalization error bound for linear regression into this kind of linear approximation. So as long as your initialization region is small enough, or like if you consider infinite width limit, then like you have some like qualitative understanding of the generalization in deep networks. The one exception is the normal bound. Normal bound is valid for every W. However, it is well known that the normal bound is exponential. So this is widely believed since since like 20 years ago that the globally valid bound for deep neural networks will be exponential in the depth. This is why people view deep neural network to be intractable, because a rigorous bound holds for every W rather than the initialization area of W is typically to believed to be exponential. However, our bound, like we can show that our bound improve this bound exponentially via the inequality log x smaller than x. So from a theoretical computer science viewpoint, there is exponential separation. So if we impose strict low rank or exponential decay eigenvalue condition, then in our examples in the paper, we show that there is strict separation, exponential separation between the wider belief of exponential normal bound with our effective rank normal bound. And so this is like a very concrete evidence why technically this bound is a significant improvement to existing global valid bound. Okay, a second comparison is to the number of parameters. So clearly, because effective rank is smaller than the ambient dimension, so our bound is naturally better than the VC dimension bound. We replace this like ambient dimension with the effective rank. And we improve this exponential bound into the polynomial bound. And the third comparison is to this NDK line of literature, which is like the most popular approach. It's like you identify an initialization point, and within this very small initialization region, you have like a linear approximation, so you can apply the linear theory to the deep neural networks. However, it is widely understood that like NTK is for the lazy training regime, means that like there's no feature learning and nonlinear dynamics, because our bound can be understood as a dynamic NTK along the trajectory, because our bound is valid for every point simultaneously. So basically, along the training dynamic, at every point, you have a generalization, characterization, through that envelope. And finally, the final characterization will be far from the initialization. So in this way, we are able to explain the dynamic of feature learning. Feature learning means that like we can explain that initially we compress the feature a little, and finally we compress the feature a lot, and the bound is feature aware, rather than using fixed frozen feature. This is like NDK is a frozen feature theory, but our theory is dynamic pointwise feature theory. Finally, what I want to explain is like this notion is also stronger than like the implicit bias literature, because basically we replace like the norm of the weight to the more advanced notion of effective rank, and also replace sparsity to the feature aware complexities. So these are like the 5 comparisons we want to make. So we eventually improve the exponential normal bound, and also replace the ambient dimension VC bound into pointwise effective rank bound, and also turn the NTK, which is a frozen feature theory, into a pointwise dynamic feature theory. And finally, this is fundamentally different with the statistical convention using sparsity or weight, because now the compression is in the feature space rather than in the weight space. So essentially, we do not control the weight complexity, but we control the active subspace of features and active subspace of features. This is so-called Grassmannian manifold in differential geometry language. I think this kind of thinking is like control the complexity of active subspace of feature matrix rather than the unbounded space of the weight. I think this is like a very clean idea to incorporate all this geometry into deep learning theory. Okay, so I want to give one sentence summary on the part one. This is like because many people have said like compression is intelligence. So our conclusion is it's a more concrete positioning of this idea, that is pointwise feature compression is intelligence. So we not only tell you compression is intelligence, because all this sparsity, all this low rank, all this weight, all this Kolmogorov of complexity, outcomes reader, all this compression. But we are telling you that compression, here compression we mean pointwise feature compression, and pointwise is rigorously defined as hypothesis-dependent complexity. That is like we provide even loop rather than a scalar bound, and the feature compression is made rigorous as the layer-wise learned feature spatial compression. So the bound is like depends on the bound depends on the layer-wise learned feature and depends on the eigenvalue only through logarithmic factors. So essentially, this is just like the number of the eigenvalues that's above a hard cutoff threshold. And to prove this bound, we need 3 innovations, and each innovation is, I think, it's like brings new language tools into statistics and machine learning. The first innovation is that we traditional statistical learning theory use Talagrand's super Riemann of stochastic process theory, the so-called generic chaining, as the central tool. So here we replace the notion super Riemann of stochastic process into pointwise envelope of stochastic process. Okay, so this is a fundamental change of mathematical topic. It's like we change the area super Riemann of stochastic process into the new topic, pointwise envelope of stochastic process. So this is the first innovation. The second innovation is for Taylor expansion. Because Taylor expansion is fundamentally infinitesimal approximation. You must control the radius or the Hessian or the higher order Hessian to make your approximation valid. So we replace all the Taylor expansion by exact telescoping sum. So this is like the so-called non-perturbative expansion rather than infinitesimal Taylor expansion. So this is the second thing. Basically, I think this is for nonlinear system. So how to replace Taylor expansion than something that is more reliable and valid non-perturbatively in finite scale. The third thing is like what I have mentioned, because we do not want to compress the weight space. We want to compress the feature space. So feature space means the meaningful eigenvalue directions that are non-zero. And the meaningful eigenvalue direction is called the active subspace. Okay, because we want to control the number of minimum eigenvalues, so we want to control the rank of the active subspace, and covering like the complexity of this active subspace is exactly covering the global Grassmannian manifold, because Grassmannian manifold is defined as the collection of all rank R subspace. So although you do not know what is particularly the right active subspace, but if you have an additional cover of all possible active subspace, then you are able to get the bound. So this is kind of introducing the traditionally continuous differential geometry language into this finite example bound. So this is third innovation. Okay, so the first innovation is for probability and stochastic process. The second innovation is for calculus. The third innovation is for differential geometry. So after introducing all these 3 steps into the traditional generalization theory, we are able to prove this one. Okay, so now like the part 2, I would like to particularly discuss these 3 concrete steps. There are some background. So first, like this is our object to study. We want to study the generalization gap, which is the difference between the test error and the training error. In particular, the test error is like if the loss function is f, and Z is a random data. For example, in supervised learning, Z is the input and label pair, X is the input, is the feature, and Y is the label. And I is something, for example, if the prediction of like f on x is close to y, then the loss function may be small. So in general, like this IOFZ is like a general like characterization of the learning setting. We date back to Vapnik. Vapnik uses the same notation and call this a general setting of learning. So we use this notation as well. And the generalization gap is basically the difference between the expectation of the loss function over the random data minus the empirical average of the loss function. So this is called the generalization gap. And the goal of traditional learning theory is to show that the training error like is small according to the uniform convergence criteria, that is control this error uniformly over every function in the function class. Okay, so this is like the so-called uniform convergence of the super Riemann of empirical process. From Vapnik's language, this is called uniform convergence. Also from people studying VC dimension and computational learning theory, that's the distribution-free learning theory. So basically, people care about this kind of like what is like the error of the worst case F in the function class. So clearly, like this is too bad compared with our result, because our result is the pointwise envelope of this like generalization gap. However, the uniform convergence will control this super Riemann. Also, like that's also why like we want to advance Lagrange theory on super Riemann of empirical process, because like this like object is exactly this like generalization gap is also called the empirical process, and so the super Riemann of empirical process is like uniform convergence will be too coarse for our goal. There are other possibility, for example, algorithmic stability, which is like algorithm dependent. Okay, so stability is similar to our concept because stability is also algorithm dependent, similar to our hypothesis dependent bound. However, stability is a distribution free notion. So stability takes super Riemann over the worst case distribution. So they are also very difficult to prove meaningful bound for deep neural networks. And finally, the closest philosophy to us is Pack-Bayes. Because Pack-Bayes is like trying to bound the generalization gap for a particular posterior distribution Q. That is like Pack-Bayes will like bound, like Pack-Bayes will give you different generalization error bound for different posterior Q. So this is very similar to our pointwise envelope. However, this Q is not a point. This Q is a surrogate. For example, this Q is like a centered Gaussian distribution where the center may be F. However, you still have this like a Gaussian perturbation and approximation error. So in this sense, Pack-Bayes is also a surrogate. So we know that all these traditional statistical learning approach, they are all the worst case or surrogate versions of the pointwise envelope. And in this work, we study the pointwise envelope directly rather than relying on only worst case or surrogate version. Okay, so this is like the motivation to study this envelope. So we define this pointwise generalization framework where we want to define a competitive function f and show that with high probability uniformly over area f, simultaneously we have that the bound is scaled with like inverse scaling with the sample size, but proportionally scaling with like the complexity at the function f. So we call this simultaneous point envelope or pointwise convergence or pointwise generalization in our paper. So the left-hand side is like the pointwise gap definition. That's the objective study. The right-hand side is the pointwise competitive function of f, and this should be uniform over area f. And the message is that the pointwise generalization truly infers test error from training error, giving only a fine example. And this is a new paradigm. So this is actually trying to replace uniform convergence to pointwise convergence, replace the Pack-Bayes from surrogate theory to an exact theory, and replace like Lagrange empirical process theory into a pointwise envelope theory. So each step is actually like the advanced, widely established convention. So how can this be achievable if like the problem is so difficult? However, like we luckily identify that it is possible to achieve this by introducing this notion called pointwise dimension. This pointwise dimension originates from like the fractal geometry literature. So basically, like intuitive, the meaning is like the prior mass accumulated as a localized metric ball centered at F. So basically, it's like also like if we have the uniform prior, then it's like the log ratio of the volume. So I would like to give you 3 different ways to understand it. First, like this is stronger than Occam bound. Because Occam bound is like a pi f. It's like a point f inside the prior. Hi, now we have a ball. So this is like a continuous version of Occam bound. Occam bound is only for countable space, but this bound can hold for incountable space. So first, this is better than Occam. Second, like we can understand this as like the pointwise version of curving number, because we saw that this like a log volume ratio, like if we take a worst case over F, then this is a canonical curving number. If you take a pi to be the uniform distribution and take the superior over F, then this is exactly the definition of a canonical curving number. Okay, so this bound is always also better than any curving number approach. So we prove that like the bound we approved is like unable to recover from any curving number based approach. Third is like which is like the most direct like motivation is like from generic chaining. So because if you take a superimam of a function integral of this, then that's called a generic chaining. The merge, or like more particularly the majorizing measure formulation of generic chaining. So basically, like from these 3 angles, the curving number, generic chaining, and Occam bound, like we know, like this may be the right measure for the general nonlinear generalization paradigm. However, we will also like to show you that like actually the most simple intuition to prove this, and also the initial way we identify this through Pack Bayes. We prove this through Pack Bayes, and only after we prove the initial results through Pack Bayes, we give you several interpretations. So although I already give you 3 different interpretations, here it is the Pack Bayes being the original motivation for us to first discover that this bound works. After we use Pack Bayes to discover that this bound works, we give you several interpretations. But I think Pack Bayes remaining the most effective way to understand like what we are doing. Okay, before we discuss the result, I want to give you some notations. This notation technical, basically we define the observed sample S and ID gauss sample S prime. And we use this notation like PS is like the empirical average, PS prime is the ghost average, and this P and this like PG is the population average. And we also define the mixed empirical gauss matrix and the population empirical, and also so this is like the empirical population matrix and also purely empirical matrix. So first, like all these distinctions, they are technical. So for technical strength, I would say that like using Gauss example is like similar to using population distribution, and both are weaker than only using like the empirical example. This is about whether you can compute the bound from data. So I don't think this is a central question in our work, because here the work is to give you rigorous generalization error bound rather than guarantee that all the bound can be evaluated and computed from data. Okay, we do give you a condition, we do give you minimum condition to transfer from the Gauss sample bound into the empirical sample bound. We have that part, but I don't think that that's like the most important conceptual message in this work. This is like I would say like this is also superior to the observability and uncertainty phenomenon physics, because what we discover is that if you want a global bound, if you want a supreme bound, then you can only use empirical, fully observable matrix. However, as long as you want to pointwise bound, we found that at the general level, at the empirical process level, you must use both the Gauss distribution and the empirical distribution. This is like you cannot simultaneously like precise position and full observability. So this is still like a post as like an open investigation. However, like, I emphasize like first this is technical, and not like central to the main message. However, still substantial. I believe this gap may be one of the most interesting phenomena in this work. This gap may even be more interesting than many positive results, because this shows that you cannot simultaneously have precise position and full observability. Okay, so after having all this kind of preparation, we are going to state our general theory. So this is theory is so here here is alpha is the approximation error, and we also have this integration from alpha to square root 2 on this pointwise dimension. So so here later I will show how this bound recover outcome, homograph complexity, and Parker bias, and also strength, advancing genetic training to obtain pointwise rather than uniform control. So you can understand. So first, compared with Parker bias, because we have this radius, so we turn Parker bias from surrogate to precise, and turn homograph complexity and outcome from countable to uncountable. But on the other hand, we remove the super Riemann notation in genetic training. So you can equivalently you can understand that the meaning of this bound is that we show that with the help of Gauss example, we can turn genetic training from a super Riemann theory to a pointwise envelope theory. I think there are also a lower bound showing that in the worst case, genetic training function is a lower bound for the empirical process. It means that the bound is a minimax tight. Means that if we insist on this kind of super Riemann regime, then this bound is already tight. What we want to prove is that we want to break the worst case regime to consider the really practical regime. So this is how this bound is tight, but also quite the upper bound is tight in worst case, but also a good starting point to study point generalization. And so this is the Parker bias interpretation, and which is the most natural interpretation to understand this result. So first, you have a Parker bias for a general posterior. Then you consider what is the approximation error of your posterior Q and the hypothesis F, and you can optimize the posterior Q, and you get this. Okay, so if you understand this, then you can prove this result in 4 lines. So you have Parker bias, right? Parker bias is a surrogate of Q, and you also want to optimize the approximation error of Q to F and the generalization error bound of Q. So if you balance those simultaneously, you can turn a Parker bias bound on simultaneous posterior Q to a pointwise envelope on simultaneous point F. But here, because the left-hand side involves both population and empirical, so your matrix need also involve population matrix. So this is the technical point. So okay, so if you understand what I just described, it's you first have a Parker bias bound, and you balance the approximation error and the generalization error to get the pointwise bound. Then you understand that the basic version of this bound can be proved in half page. So although I think this is a new perspective, but proving this result is not difficult, and proving the integral result is more involved. You need to spend I think maybe 7 pages to prove this. However, because this is this bound is stronger by understanding that this part is actually decreasing with alpha. So this bound is initial bound, and that bound is a more advanced bound with matching lower bound. We prove the integral bound because we want to match the lower bound. However, this bound itself only requires half page. Okay, and also we need to have this Gauss example. Without the Gauss example, we cannot achieve this. Okay, so this is the first part result. And so here, I want to comment that first, we have this kind of fine scale epsilon. So this is different with NTK. So this bound holds for simultaneous for area F. And it's we have this local geometry as NTK, but simultaneous for area F. So now we do not require initialization because we already have simultaneous pointwise envelope. And I also want to mentioned that like if epsilon is equal to 0, when the epsilon is equal to 0, this is outcome razor. So we can say that like this bond actually improve Kolmogorov complexity or outcome razor into incountable continuous space. And Ilya actually gave a talk on the observation and generalization, I think a few years ago, saying that everything can be explained by the so-called like outcome or Kolmogorov complexity. So here is right on one point, that is the pointwise, but wrong on the other point, that is like you also need the finite scalable. So outcome is already a pointwise bond, but this bond improve outcome into pointwise finite scalable. So this is like why I say like Ilya is right on one point, but wrong on the other point. Okay, so and this is the two most crucial features. If we only have finite scale, then that's a Calvin number. If we only have pointwise, then that's Packer Bayes. We turn Packer Bayes and the outcome to a finite scale. So this is why like we are above Ilya's observation, and we turn generic chaining and Calvin number to pointwise. This is why we are above statisticians. If you only have the first, then it's like statisticians, and if you only have the second, then that's like the Ilya and the Packer Bayesians and the compression people. But if you have both, then that's our theorem. And now we have the principle that is like, because we have this kind of simultaneous pointwise envelope, then as long as we have like, we find the compression at the desired f, then we have low generalization error. Okay, and this is like the first part. The part 3 and part 3, I will explain quite shortly. Okay. Oh yeah, yes. So okay, yeah. So it's pi is crucial. So first, like there is traditionally pi is in a minimax formulation, min pi super f. So that pi is well defined in generic chaining. However, here there is no universal good pi because there is no free range. You cannot find a pi simultaneously good for all f. In our theory, our construction is based on uniform or Gaussian. So it's like what we do is that we cover all possible active subspace. So our construction of pi is based on uniform and Gaussian. This is for the answer. Because there is no simultaneous pi good for all f, so we use a uniform or Gaussian to construct the desired f to prove the bound in slide 1. So final goal is slide 1. Uniform construction is already good to give the bound in slide 1. Okay, so the second part is like, first part is the stochastic process. The second part is about calculus. So we do not use Taylor expansion. We use telescope sum. With this telescope sum, it's like a layer-wise telescope sum. What do we have? With the layer-wise telescope sum, we can show that the empirical matrix is bounded by a pointwise linear matrix. Because if we have this, and then applying Cauchy-Schwarz, and also so because here this pointwise expansion keep this Nernst feature, the inner product of Nernst feature and the weight. So we know that it's basically it's if we use this telescoping sum and combine and taking the square, if we're taking the square, then this is a quadratic form with the feature matrix to be the gram. So this is how gram appear in our bound. Because if we take the telescope sum, then we keep this inner product, and this is the most crucial thing because here, although the matrix is not linear, although the function is not linear, although the matrix is not quadratic, but the matrix is pointwise quadratic. With the changing, this is like a quadratic matrix with moving dynamic gram. This is what we get from this non-perturbative expansion. We get an approximate pointwise quadratic function with moving gram. And all these are using just telescoping sum and Cauchy-Schwarz inequality. So all these do not require approximation or calculus or infinite or infinitesimal approximations. Okay, the third part is I have a slide. So because we want to prove the complexity of the effective rank of the feature map, so we want to cover the active subspace rather than the weight. So this is different with traditional statistics. Traditional statistics cover the sparsity or low rank space. So that's like a common number of the weight space. Here, what we cover is not a weight space. It's like the inner product has two parts, right? Have W and a feature. Traditional statistics want to cover the W part. We want to cover the F part. If we want to cover the F part, then that's like cover the active subspace. And covering active subspace is like the theory of covering the Grassmannian manifold in differential geometry. So applying this result, we have this like the complexity is equal to the local linear complexity plus global subspace selection cost. Okay, this is how we prove the bound. So this like input dimension complexity is the covering local bound, and this output dimension is covering local, is like the covering linear cost. This like input dimension is the cost of the principal subspace collection. So it's quite symmetric, right? So quite magic, because it's like magically by analyzing not only the linear geometry but also global geometry, we understand that the additional cost of a neural network is this. So this is what you already know from NTK. So the first part is the familiar NTK part. The second part is the dynamic cost to make NTK pointwise. The dynamic cost of NTK pointwise is similar to the familiar NTK, with the only difference to replace the output dimension into the input dimension. So this is quite like a magical in the sense that neural network has a very beautiful property that the additional cost to make NTK dynamic is comparable to the NTK cost itself. And in this way, we can conclude that neural network can be explained like in this fashion if you believe that there is very good feature compression. Okay, and this is like the summary. So we have the first principle that is like we have the pointwise even loop. The second principle is like we replace the calculus with the telescoping sum. And that's like the moving gram pointwise quadratic matrix. The third is like the additional cost to make NTK dynamic is similar to the original NTK cost. The only difference is to replace the output dimension by the input dimension. So by these three principles, we can establish the sentence. Pointwise feature compression is intelligence, with pointwise means hypothesis-dependent complexity, and the feature compression is the layer-wise learned feature spectral compression. And this is like the main conclusion of the talk. There are also experiments. So in the experiments, we observe that like our bound is the only bound that decreases over-parameterization, and all the other bounds which are like orders of magnitude like larger, like the exponential bound and also VC dimension bound, they increase with the parameterization, but we decrease with the parameterization, and we improve like this like exponential bound by 10 to the 9 order. And also like we also observe that like we observe like typically like the compression is 1/300. So if the effective rank is only 1/300 of the ambient dimension, so there is indeed feature compression. And finally, we also observe that in the ResNet, 19% of the layer is 0 rank. So in fully collected net, like the feature compression is at the scale of 1/300, and in ResNet, like 19% of the layer actually have 0 rank. This is why like we have like a significant like a feature reduction. I have to say that like the bound is still not practical. The bound is still much larger than the still like far from like a really like a precise characterized generalization. However, like because we characterize this because we decrease with the parameterization, so this is a meaningful initial step. And finally, we found that this HGD training dynamic, HGD will convert to the points that have low pointwise dimension. This is why like the final is like you see like the initial point may have like a very high pointwise bound, but the final point will have very good pointwise compression bound. Okay, and in this work, we do not study optimization, and we do not study CNN and RNN, and also we do not study what's the structure in the data. But I think all this like the future directions. So this is like conclusion. Like we have the theory and the empirical findings, and like I would like to stop there.
So questions?
Hey Yunbei, thanks a lot. It's very interesting. So I just want to confirm one thing. So from a high level, I think what you essentially want to do is, because minimax is too pessimistic, and the global covering number is usually out of reach, especially for very complex things. So you just essentially want to replace the global covering number with the local covering number for whatever F you are training on. Is that correct?
Yes.
Okay, so can you go back to the main theory page? I also have a little bit of question for that. Yes. So I think I always been thinking about, so essentially because your result is specific for every F,
yes.
So what does exactly the function family like Masco F is doing?
Okay, so the prior is the unbinding prior. The prior is the unbinding prior. The prior needs to be supported on the whole F. So here, I think prior is on F. The prior needs to be supported on the whole F.
But you only, for each small f, you only need local properties of the prior. You only concern about the prior, like this B around every f.
Yes.
Everything else is out of your idea anyway. So why do you still need to introduce this Masco f? It's just for the sake of completeness?
But imagine, okay, so if F becomes larger and larger, then the weight will be proportional decrease, right? So if F's volume expands, then the proportional mass of the local prior also decrease. So you are right that I think it's the influence of the influence on this local bound by F is much lower than the worst covering number, but still it is influenced by the F. And I think in our bound if you have feature compression, the influence on the radius of F is logarithmic. So if you note our definition in the effective rank, you will observe that there's still this radius term, right? But it's the effect of the radius will be logarithmic. I think I don't know whether this answer your full question, but it is by definition, because the support of pi is on the whole F. So if F becomes larger, then although you are right that we only kept the local covering, but with larger F, this denominator will also be smaller.
I think it's with a larger F, you will be struggle to define a pi that actually works for every.
Yes.
Okay, so maybe one last thing is, it really reminds me of the recent trend for base non-parametrics is where you do the fractional posterior. Essentially, you no longer need covering number. You just need a prime mass condition, and then you can guarantee convergence. So to me, it seems like prime mass condition care about the local properties and maybe related to local covering number you are discussing here, but I'm not exactly sure of the relation. But I just think I want to say is I highly stand with your point of view is we do not want a global control because we have essentially reached the limit of what we can do with global control with the minimax theory, and we want to get rid of that, and we can deal with more models. Yeah.
I think this is excellent comment, and this is the first time I get this feedback because I can answer you that okay. So first, the fractional common number is developed by my postdoc advisor and Jen's doctoral Sasha, and there are also some other previous work, but they spend a lot of time studying that. So a common number is the worst case. Fractional common number is also worst case. Fractional common number is replace the number by fractions by prior, but that's also worst case. So what you are saying is extremely interesting because our bound is both fractional as well as pointwise. But I think Pack Bayesian is a posterior that is pointwise. And if you are mentioning fractional Bayesian, then that should be very similar to what we are doing here. Maybe the only exception is that we care about deterministic F, so we have approximation error and the radius, and maybe the pointwise fractional Bayes is still trying to generate a posterior because essentially I think Bayesian inference is for distributions rather than deterministic F.
Yes, for distributions, but I think the high-level idea is same.
Very similar, yeah.
Because you extract some point estimate out of the distribution, it might well end up being the exact same bond.
Yes. So this is a very great feedback because this is the first time that I heard something that is both fractional as well as Bayesian. So I agree that will be very similar to the result here, although clearly there should be some distinctions, like for example, deterministic versus distribution. But the high level idea is very similar.
I think it's technical level will definitely is different, but I think the idea will be more important.
Yes, and I think what you mentioned is should be better than fractional common number. So now I only discuss how it improves the fractional common number, but I believe this kind of fractional local Bayesian prior should be even already like a long tradition that trying to have this high level idea.
Yeah, thanks a lot. I maybe leave time for others.
Other questions? By the way, finish the QA. We have a group photo. Okay, so stay with us.
Yeah, very interesting talk, and yeah, definitely the pointwise approach is very insightful. And one thing I wonder is that basically now you have the pointwise generalization bound, right? So then how here is still not directly connected to optimization yet. That is kind of like saying that for each parameter point, actually we have this kind of very good generalization guarantee here. And yeah, I'm trying to think about how to connect this to optimization, saying like, when I do the training, I get this optimization trajectory. And then if you look at the each point on this trajectory, then we indeed have this guarantee, right? And how do we know, along the optimization trajectory, whether we have some analysis on the trend? Like for example, can we show that with the optimization going, we can get better and better generalization?
Yes. Yeah, I want to answer this from 3 sentences. First sentence is that this is the main result, not the other results, and my favorite part is actually the third part. So it means that there is a lot of room for this more kind of concrete analysis on the neural network parameterization rather than just this abstract theorems. The second sentence is means that although I spent a lot of time to explain that this is mathematically non-trivial, however, the most involved part and also the most insightful part is actually the hidden third part about this active subspace, where I believe there is a big potential to combine with optimization, but we haven't done anything in this area yet. The second is, so there's a big potential and also hidden from what I present today. The second thing is that we have these experiments. This experiment exactly we track the track the effective rank of SGD across the training. So empirically, we do observe that initially this kind of the pointer dimension may be 10 to the 8th, but finally the pointer dimension will be much smaller and smaller than the sample size. Eventually, it's much larger than the sample size, and so this is also the distinction of this the hour bound and the VC dimension. So basically, at the initial point, the SGD's pointwise dimension is essentially VC dimension, but at the final point, SGD decreased from 10 to a 10 to 10 to a 7. That's also I say that the average compression is 1 over the 300 in our experiments. So exactly explain both the trajectory of SGD and the difference between R bound and VC bound, and also this average compression of 1 over 300.
Well, thanks, Yunbei. Great talk. So I have 2 questions. So first, regarding the lower bound, could you turn to the lower bound page?
Okay, lower bound. Okay, the generic shading lower bound, not proved by me, proved by Calaguan.
Right. So yeah, so it seems like the lower bound is also pointwise, or I think I'm.
Sorry. So this is SUP over F.
Right. Okay, that makes sense. Yeah, because lower bound.
Yes.
If I'm fine to sacrifice a point, then
Yes. Yeah. So this is a traditional lower bound by Calaguan, SUP over F.
Okay, good. Thanks very much for the clarification. So the other question regarding the upper bound, I think the interesting thing is that I think you mentioned that you use ghost samples, and it's somehow important here.
Yes.
I think another technical aspect is that people have been studying things like contrastive learning, and there is this idea of conditional mutual information.
Yes.
And they also derive generalization bounds from that. Also, actually, I have seen works that use Bayesian combined with this. I think conditional mutual information with and then they can do experiments that actually show, I think, some useful generalization. Like like their errors are like small, like not like vacuous. So I just wondering, like, how do you compare your work with these this trend? And
so first, like the theory is different. In our paper, we have this comparison with conditional mutual information framework. So conditional mutual information framework also into this Gauss example, but again, like the mutual information is for random posterior rather than for pointwise. So we bound the deterministic type, and they do not have this bias variance trade-off step. So fundamentally, like that's still and also like conditional mutual information is not so much different with mutual information. Conditional mutual information want the bound to be the prior to be symmetrically depends on S and S prime. So we also have a generalization of the theorem where pi can depend symmetrically on S and S prime. So theoretically, I don't think conditional mutual information is a big leap by unconditional mutual information. However, it's like there are similarity in ideas. But empirically, conditional mutual information is very powerful, and the distinction is like our main theorem is stronger, but our final evaluated bound is in this Riemannian dimension, our real main results on page 1. So although this theorem is stronger than conditional mutual information, in the sense that it's deterministic rather than like a surrogate. However, the final bound, the bound on page 1, is not as strong as those non-vacuous Bayesian literature, because we already go over the step 2 and step 3. And prove the simplified version of this, like in whole page. That's also why I encourage you to read our paper, because if you read our paper, this very interesting theorem can be proved in whole page. The whole paper is 111 pages. So the most involved part is like there are still like many mystery that we can try to explore in the future.
Great, thanks.
Other questions from the audience? Okay, so if no more, so let's thank the speaker and have a group photo together. Yeah, please.